In this video, I want to derive the singular value decomposition for complex matrices. Now, you can follow the same steps that I'm going to show you in this video for regular matrices, matrices with real entries, but I'm specifically going to deal with matrices with complex entries. So in my calculations, in my computations, instead of using the regular transpose, I'll be using the Hermitian transpose. So just keep note of that and we'll begin. So to start off, let's consider an n-bind matrix A, which, by the way, when we take the matrix A and multiply by the Hermitian transpose of itself, will become Hermitian. And this is because if we take this matrix, what we have here, A transpose A, if we take this matrix and apply the Hermitian transpose, we get the same matrix that we started off with, right? Which is why it's Hermitian. And we also know that the nullity of A transpose A is equal to the nullity of A because both A transpose A and A have the same null space. And since both of the matrices have the same nullity, their rank should also be equal because of the rank nullity theorem. Now, how do I know that both A and A transpose A have the same null space? How do I know that? Well, it's not that hard to see. First, let's set this equation up, right? This homogeneous equation. Basically, you'll see that here for x basically belongs to the null space of A transpose A, only then can we have this equation equal to 0. Now, what we can do is use the associative property and group AX together. This way, what we find is that for all x belonging to the null space of A, right, AX is equal to 0. Of course, we know that. However, if AX is equal to 0, then A transpose multiplied by the 0 vector is equal to 0. Therefore, if there exists an x that belongs to the null space of A, x must also belong to the null space of A transpose of A, all right? This is basically just saying that all the set of values for the null space of A are a subset for the null space of A transpose of A, all right? Now, I've got this, the first part down. Now I want to show that the null space of A transpose of A is a subset of null space of A. This way, I'll just prove that null space of A is equal to null space of A transpose A. Now, what I can do next is simply take the equation that I started off with, right? Where for all x belonging to null space of A transpose A, this equation equals 0. This expression equals 0. And this time what I can do is multiply both sides of the equation with the Hermitian transpose of x, okay? And here's why. Because I can rewrite this like something like this, all right? And some of you guys will notice that this is just the complex dot product, right? AX is a vector, taking the Hermitian transpose of a vector and then multiplying it with the vector is just the complex dot product. And so I can just simply write it like this, right? Where I have the magnitude of this vector AX squared. And if I take the square root of both sides, I get something like this, all right? And the only way this magnitude can be 0 is if the vector AX is the 0 vector, all right? And the only way AX is going to be the 0 vector is if X belongs to the null space of A. Therefore, the null space of A is equal to the null space of A transpose of A. Now, let's start off simple. Let's to basically construct this decomposition, our end goal, to reach our end goal, what we can do is utilize information we already know. So let's use orthogonal diagonalization as our starting point. So we know that Hermitian Hermitian matrices can orthogonally be diagonalized, right? Into something like this, where we have the matrix V, the matrix C, and the transpose of V. So basically, V contains the orthonormal eigenvectors of A transpose A as its columns, and D contains the eigenvalues corresponding to those eigenvectors. Now, we already established that rank of A is equal to rank of A transpose of A, right? However, the rank of D is the same as the rank of these two matrices. That's because D is similar to A transpose A. Now, since D is similar to A transpose A, D should also have the same rank as A transpose A, which is why we have something like this. So another thing to note here is that the eigenvalues of A transpose A are actually equal to the square of the singular values. Now, I'll talk more about singular values in the next couple of slides. If this doesn't make sense to you, just keep up with the pace. You'll soon find out. But let's just say that rank of A is equal to some arbitrary value k, all right? And we know that if rank of A is k, then the rank of A transpose A should also be k. Now, if we arrange the eigenvalues of A transpose A in a descending order, we get something like this, all right? Where now again, we noted that rank of the matrix is equal to k, right? So there will exist k number of non-zero eigenvalues, and all these eigenvalues will be positive. It's because the matrix is Hermitian, so all these eigenvalues of A transpose A will be positive. I'm not gonna show you guys how and why they're positive, but just know that all these are gonna be positive. And basically the eigenvalues after the k, after the kth eigenvalue, all the other eigenvalues are just going to be 0. All right. Now, why would it be 0? Well, an important thing to note is that we know that square matrices, when they're not invertible, their eigenvalues will be 0, right? And same thing here for A transpose A. It is possible that A transpose A is not invertible since A transpose A was derived from the matrix A, which is a rectangular matrix. And since the rectangular matrix has a certain non-trivial null space, the resulting matrix A transpose A will also have some sort of a null space. And therefore, we will have the eigenvalues of 0. So also, given that A transpose A is an n by n matrix, it is orthogonally diagonalizable if and only if it has n number of orthonormal eigenvectors, and it has n number of corresponding eigenvalues. So if you look at right here, right, we have k number of eigenvalues here all the way up to n number of eigenvalues. So since we have n number of eigenvalues, not necessarily distinct, because of course some of them are going to be 0, some of them might be positive and equal to each other, but we know that there are n number of eigenvalues corresponding to their orthonormal eigenvectors of the matrix V, according to the orthogonal diagonalization. Now, some of the I already mentioned this. I already explained to you guys, right, that we have these eigenvalues of 0 because of the null space of A transpose A. Now, if we take the square root of the eigenvalues right here, we actually just get singular values, right? Because the square of the singular values is equal to the eigenvalues. So now that we have now that we know how to get the singular values, let's see what we can do with singular values. So to do that, what we need to first do is construct a matrix with orthonormal vectors. So let's start off with the singular values. And we need to realize that they kind of act as the eigenvalues of A. They don't really act like eigenvalues of A, but they kind of do. I'll show you guys how that works because it's pretty cool. It's not the way you've seen it before, but it's pretty cool. I'll show you guys. But to show you guys, let's start off by establishing some parameters. So let V be the orthonormal eigenvector in the matrix V and in the matrix V. So if I take any arbitrary eigenvector from the matrix V, and if I apply the matrix A if I do the transformation of matrix A applied to V, and I take the dot product, right? So basically, this is just the dot product of AB. And if I rearrange that, I get something like this, right? This can just be rewritten as this, right? We're using the property of transpose. And now that we have this, if you notice, we have A Hermitian transpose multiplied by A. And we know that this, when multiplied by with an eigenvector taken from the matrix V, that is just equal to the eigenvalue of A transpose A multiplied by the same eigenvector. All right, so this can just be written as this. And since we have this, we know that the eigenvalue of A transpose A is just equal to the square of the corresponding singular value. And so after we get that and do some little bit of rearrangement, we get something like this where we end up with a dot product of the eigenvector V. And finally, we can rewrite the dot product of the eigenvector into something like this. Now what we can do is compare this, what we started off with this, and we notice that we can end up with this equation, something like this, right? Because if this is a dot product, it's just going to be the magnitude of the vector AV squared. Same thing here, we just take this, put it here, and what we can do is square root both sides and we get something like this. Now, this kind of resembles the classic eigenvalue eigenvector equation, right? We have our matrix A here, we have the eigenvectors B on both sides, and then we have the eigen. But the only exception being is that we're dealing with the magnitude instead of the actual transformations being applied to the vectors, right? So it's not exactly the eigenvector eigenvalue equation, but it's kind of close, you know, it kind of resembles that equation. So it's still pretty cool, right? We have a non-square matrix, we have a rectangular matrix, and we can still find an equation like this, which can be used to easily find out at what value this vector is being scaled. It's pretty cool. Now, we know that V is an orthonormal vector, and since it's orthonormal, its magnitude is just going to be 1. So basically, this whole equation just turns out to be this right here, which says that the magnitude of AV is just the singular value. Now let's see how this can help us with actually finding the singular value decomposition. So first, what we have to do is construct the individual orthonormal vectors U, which is just the vector AV, but normalized. So if we want to find the vectors U, the ith vector u. And what we can do is just multiply the vector AV with the reciprocal of its magnitude, right? That's how we normalize vectors. And from the previous slides, we established that the magnitude of AV is just the singular value, right? This epsilon right here, singular value. So what we can do is rewrite this as this. And basically we can just take all the vectors, all the ith vectors AV and basically just divide it with its corresponding singular value, and we'll get the vector u. And what we can do is align the vectors in columns of a matrix and call that matrix u. All right. Now that we have constructed this matrix, oh, note that we have constructed this matrix only up to the kth orthonormal vector here, u. And that's because if you remember, the rank of the matrix A transpose A is k, right? And after the kth value, all the other eigenvalues were just 0, right? So we need to somehow take that into account and construct a full matrix U. So in order to do that, what we can do is consider the values of I, right? We have the vector ui, right? So consider these values I after the value k, and basically between k plus 1 and n, consider those corresponding vectors u. And if we wanted to find u, right, in within this range, then what we need to do is find vectors that are orthonormal to this set of vectors right here, okay? And how do we specifically do that, right? Because remember, our purpose of creating the matrix U is to create a set of eigenvectors in its columns that are orthonormal to each other, right? And basically to create additional set of orthonormal vectors, what we need to notice is that this matrix right here, right, the columns right here represent the column space of U, okay? And since we have the column space of U, if we wanted to find an additional set of vectors that was orthogonal to the column space of U, that was orthogonal to all these vectors, what we need to do is find the null space of U transpose, right? Because we know the null space of U transpose or orthogonally complements the column space of U, which is why if we find the null space of U transpose, we should find all the remaining set of orthonormal vectors that can then be pushed into the matrix U. And this allows us to construct a new matrix, which gives us a full perspective, a full view of basically by just giving us all the eigenvectors, right? U is a vector in Rm, right? And we have m number of eigenvectors. So there's going to be an m by m matrix. And we just need to know that all these additional vectors that we didn't have in the first matrix are just, they just belong to the null space of U transpose. Now, let's get to the part where we actually construct the decomposition. So let sigma be an m by n diagonal matrix which contains the singular values in its diagonal entries. So sigma should look something like this, where in its diagonal we have the corresponding the singular values, right? The epsilons right here, and across the diagonal, the value of the singular values actually decreases. All right, so note that. Also, after a certain point, you'll notice that the columns just become zeros, right? In the columns, we just have zeros here. And that's because, if you remember, after the kth point, the singular values stopped being positive numbers and just ended up being zeros, bunch of zeros, right? Same thing here. Sorry, hold on. But yeah, basically after certain point, we just got a set of singular values which were zero, right? And that's because the corresponding eigenvalues of A transpose A were zero. Now, if we take the matrix U that we constructed from the previous slide and find its product with this matrix sigma right here, we get something like this. This makes sense because the matrix U just contained U1, U2, all the way to UM, all those eigenvectors in its columns. And the sigma matrix right here, well, it just has entries in its diagonals. So all the other entries are just zero. So we should just get something simple like this. And if we notice that that the ith singular value multiplied by the vector u vector by the ith vector u, then we get something like this here. We get the matrix A being multiplied with the ith vector v. So basically what I'm trying to say here is that all these other entries here just resemble this matrix multiplication here. Same thing here. This thing here resembles this. And that's because from a couple of slides ago, I showed you guys that when we normalize the matrix, not the matrix, when we normalize the vector AV, right? We multiply by the reciprocal of its magnitude, which was just the singular value itself. And so basically, if we multiply the singular value with the vector u, we know that u was just the vector AV divided by the singular value, and so multiplying that with the singular value just ends up with the vector AVI. Right, so this is just equal to this, which is why all the other columns are, which is why the columns here are equal to the columns here. And so we know that this is just u multiplied by sigma, which is equal to the matrix A multiplied by the matrix containing the vectors v. And which matrix contains the vector v, vectors v? Well, that's the matrix V itself. And so you should probably see where we're going with this, right? You'll notice that all we have to do is multiply both sides with the inverse of V from the right. And we know that the inverse of V is just V transpose because V is a matrix that contains orthogonal vectors. And doing so gives us this formula or this decomposition right here. So that's how you derive the singular value decomposition specifically for matrices with complex entries. Now you can apply this whole derivation process. Also, the same process is applied to matrices with real entries, but all you'd have to do is just replace the Hermitian transpose with the regular transpose, and I think it would just work out the same. So yeah, that's the point of this video, and I hope you guys enjoy.